ठीक है. So hybridization में क्या बोला? Pauling said hybridization में, again it's there right there in the word hybrid. Like you guys must have heard of the word hybrid pehle, right? What context did you hear it in? Anyone?
The resonance hybrid thing. I mean,
Resonance
because
hybrid, okay, but general term, like before coming to 11th grade chemistry, pehle kabhi suna hybrid? Generally,
Yes,
real
ma'am.
life
Seeds.
the genetic hybrid, yeah, exactly.
hybrids, right? Hybrid में क्या हो रहा है? You take two different okay, not two different species but two variations of the same species और उसको mix करने पे you get like some sort of a hybrid, right? So atomic orbitals may be, it's the exact same concept. So atomic orbitals that are slightly different in energies. Now this is an important bit, that they should be slightly different. ठीक है. So slightly different in energies combine to form a new set of equivalent orbitals. Okay, so these, the result of this combination, they're called hybridization. They're called hybrid orbitals, and this whole process is called hybridization. Okay. And these hybrid orbitals are the ones that take part in chemical bonding. So hybridization, it's not like you can't combine any random atomic orbital with something else. Oh, Ishita, you've answered it on chat. You said mix of two different things. Ishita, what happened? Like your mic, your video is also not on. What's up? If possible, it's better if you just tell, like if you have video or audio switched on, because it's easier. So like it'll be a real-time conversation.
Ma'am, my bandwidth is very low right now.
अच्छा, ठीक है, no problem. ठीक है, तो फिर at least see if you can use the mic. Otherwise, ठीक है, I'll keep an eye on the
Yes,
chat.
thank you, ma'am.
Okay, all right. So there are certain features, as some conditions for hybridization. कोई भी random atomic orbitals से नहीं होता है. So even if you were to create a genetic hybrid, again you will create it between same rose flowers of different colors or peas of different colors, right? You're not going to mix a potato with a rose. So similarly here also, hybridization will happen only between atomic orbitals that differ slightly in their energy. बहुत similar होना चाहिए energies. So features of hybridization: first, the number of hybrid orbitals produced is equal to the number of atomic orbitals that take part in hybridization. So if you take 3 atomic orbitals, you're going to get 3 hybrid orbitals. So if I take like 1s orbital and one, or like एक s orbital, and if I take 2 p orbitals, because I'm taking 1, 2, 3 atomic orbitals, I should get 3 hybrid orbitals out of this. Okay. Second, the hybridized orbitals are always equivalent in energy and shape. So atomic orbitals, now s is spherical, p is that dumbbell shape, different shapes, energy also like thoda sa slightly different hoga, but the hybrid orbitals that you end up with once they combine, the hybrid orbitals are all going to have the same shape, or equivalent in shape, and also equal amount of energy. Okay, so what you're basically doing is you're taking the atomic orbitals which are close enough in energy but still they're different energy and different shapes, you're mixing them up, and you're basically splitting, like you're creating 3 equivalent orbitals out of that. Okay, so hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Now, why is that? Because again, they're all equivalent in shape, right? So they can arrange themselves so that the repulsions are low, so that there's like maximum distance between the bonding pairs, lone pairs of electrons, and like the repulsions are kept to a minimum. So that makes it more stable to form these chemical bonds compared to pure atomic orbitals. And these hybrid orbitals are directed in a particular direction to have minimum repulsion between the electron pairs, abhi jo discuss kiya, and thus a stable arrangement. Hence, the type of hybridization is indicative of the geometry of the molecules. So this basically, this theory builds upon your VSEPR theory. So VSEPR is just telling you कि इस molecule में ये shape होगा, and hybridization is giving an explanation कि what is happening in the atom or the atomic orbitals to give it that particular shape. Okay? So this is basically building up on that other one. All right. Now, conditions for hybridization. First condition, orbitals present in the valence shell of the atom are hybridized. Always, 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 whenever it comes to chemical bonding, only the valence shell takes part. Outermost shells take part. Okay, so hybridization के case में भी only the orbitals present in the valence shell. So you will never have a 1s orbital of oxygen atom taking part in hybridization. Second, the orbitals undergoing hybridization should have almost equal energy. Now this was a point I stressed on pehle bhi. So like for example, if I take let's say phosphorus. So phosphorus ka atomic number is 15. Electronic configuration is 1s2, 2s2, 2p6, 3s2, and 3p3. Yeah, 285. Yeah, okay. So first point says that if at all phosphorus is forming chemical bonds, the 1s and 2s are not going to take part in hybridization. Hybridization hona hai to only the 3s and 3p orbitals are eligible to take part. Only these can undergo hybridization. Baki sare will not. Orbitals undergoing hybridization should have almost equal energy. Now 3s and 3p, they have like both of them, unka donon ka quantum number n is equal to 3. They are only differing in the L value. So because they are close enough in their energy, they can undergo hybridization. Now you will not have a 3p orbital undergoing hybridization with a 4p orbital. So 3p and 4p बहुत ही ज़्यादा difference आ गया energy में. So you should have almost equal energy. So a quick way to figure it out is एक तो n value equal होना चाहिए, like whatever atomic orbitals you're considering, or you can check that if you see n plus l, they should be equal. If not, the difference should be not more than 1. So that's like a quick hack to figure out ki acha, will these orbitals combine to form hybrid orbitals or not. Okay. So either they like if they have same n value, same principal quantum number, unka energies will be close enough, or you can check the n plus l ka value. Okay. So ऐसे. Next, the promotion of electron is not an essential condition prior to hybridization. So hybridization के पहले, so promotion of electron का मतलब, so let's take carbon for example. So I'm just gonna write it. So carbon का electronic configuration is 1s2, 2s2, 2p2. So s orbital is full and p orbital में 2 of them are filled. Okay, so I'll look at third and fourth points together. Yeah? So third point says that promotion of electron is not an essential condition. And fourth point says that it is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. So these are not necessary conditions. So like if you take carbon, it is not necessary that, like one of this electron is to be excited to, fill the empty p orbital. So hybridization will take place even though the s orbital is filled and p is like two of them are half filled. So this promotion is not a necessary condition for hybridization to take place. And in the second one, it is not necessary that only half filled. ऐसा नहीं होगा कि अच्छा S is like fully filled 2s2. So if carbon has to undergo hybridization, it's not necessary that only the p orbitals along with the 3s or something is going to undergo hybridization. Like that's not necessary at all. Even though this is fully filled, even though this is empty and this is half filled, these all four atomic orbitals can combine to form four hybrid orbitals, four equivalent hybrid orbitals. Okay, so that's what these points mean. So promotion of electron not an essential condition, matlab it's not necessary that they have to be half filled. It's not necessary that the electron has to be excited and it has to be present in all the participating electrons. Like all of that is not necessary. So it's just completely need based. You want to form four bonds, like you want to assign four places where the electrons can stay at. Fine, I'm going to combine four atomic orbitals and make four hybrid orbitals. That's all that matters. Okay. So now let's get into what kind of hybridization you observe and how they are formed and all that. Okay. So types of hybridization, any number of any atomic orbitals can combine to form hybrid orbitals. All right. It's not necessary that all of them should participate. The only criteria, as mentioned here, is that it should be in the valence shell. And second is that they should have almost equal, similar energy values. Right. So going by that,
Ma'am,
yep.
sorry,
Yeah, go ahead.
I had a doubt. Yeah. The promotion of an electron is not an essential condition prior to hybridization. I still didn't get it.
Acha.
Like, what does it mean by promotion?
Promotion matlab excitation. Excitation of the electron is not
But
necessary
even,
condition. Yep. Mitali, I think you're frozen. Mm. She's got disconnected. Sorry. Yeah, I missed your question, Mitali. There was some network issue, I think.
sorry. I don't know. I just went out of the thing.
Mm.
Sorry. Yeah. So even during when you see the promotion is basically the excited state of the right now example carbon, so carbon atom, right?
Mm.
So when it says promotion of an electron is not an essential condition, does it mean that usually doesn't have to be excited?
Yeah, it doesn't have to be excited before
Okay.
hybridization, because once the atomic orbitals get hybridized, the electrons automatic like kind of arrange themselves in the hybrid orbitals.
Yeah.
So
Okay.
yeah, excitation is not necessary prior to hybridization, because after
Okay.
hybridization anyway they are distributed
They're
as like,
gonna jumble. Yeah.
yeah.
Okay.
ठीक है. So now coming to types of hybridization. First we've got sp hybridization. Again, hybrid orbitals is very easy. You guys stop me if you already know this, then we can do a quick Q&A sort of a thing. Okay. So what do you mean by sp hybridization? इसमें क्या होता है? What is it a hybrid of?
S and P orbital.
Yes. How many s and how many p?
One of each.
One each.
One each.
Yeah.
Absolutely. And if you have one s combining with one p, how many sp hybrids do you get?
Only one, ma'am.
Yeah.
I
Array?
mean,
What was the first thing? So the
Two.
total, how many ever atomic orbitals go in, you get the same number of hybrid orbitals. So sp hybridization के लिए कितने atomic orbitals जा रहे हैं?
2.
2.
S, one s and one p orbital is going, right?
Yeah.
तो कितने hybrid
Yeah.
uh,
Two.
produce? 2. So you get 2 of these sp hybrids.
Okay.
ठीक है? So always mass is conserved, energy is conserved, atomic orbitals are also conserved. You can take it that way. So sp hybridization, yes, there is one s orbital and one p orbital hybridized to form two equivalent sp hybrid orbitals. Okay. Usually by convention, the p orbital that goes in is considered, like the pz orbital is considered to go into hybridization whenever this happens. So pz are suitable if the hybrid orbitals are to lie along the z-axis. The geometry, now because you've got two hybrid orbitals, both of them, again, to maximize the distance, like to minimize the repulsions, the geometry is going to be linear. So sp hybrid orbitals have 50% s character and 50% p character because equal parts s and p are going in, so it's 50-50, as simple as that. Okay. So here you've got the orbital diagram. So you've got a spherical s orbital and this dumbbell shaped p orbital. After undergoing hybridization, you've got two sp orbitals. This is one of the sp orbitals and this is the other sp orbital. Now each of these, of course, is going to be like a constructive and destructive, like if you have combining atomic orbitals, depending on which phase they are in, you would have like a constructive and destructive aspect of it, right? So this is how the hybrid orbitals are aligned. So where you have this is where it is constructive, so this is the positive, and this is the destructive combination. That is why the distribution, like finding the electron, so in this part is minimal. That's why this side is smaller and the side is bigger, because there is more probability, there is more electron density you'd find over here, because both the atomic orbitals, they're adding up. So when you have two sp orbitals, both of them, obviously they belong to the same atom, they align linearly with each other, SA. So if I were to show, if like let's say this is the red sp orbital and this is the blue sp orbital, this is how they'll be aligned. So the blue may right side more probability of finding electron and the side is tiny. And
question.
one
If
moment.
there's no, oh, sorry.
So the red one is aligned this way. So wherever there is constructive this thing, like wherever there is more probability of finding the electron, that is the part which is ready to overlap with the other bonding atom. Yes, Mitali.
Ma'am, you said that the larger part of the orbital, so like the larger thing, you said it has more electron density. Why is it positive?
मतलब constructive interaction हुआ ना दोनों का.
Okay, no,
So
I'm saying before interaction.
Oh, no. So this interaction, this is basically when the s and p orbitals combine.
Okay.
Yeah, each of these orbitals formed, one side is heavy and one side is light.
So the heavier region is constructive and has more electron density.
Yes, and that is the region that participates in the bonding with the other atom.
Okay.
Yeah. So that's why I drew this diagram over here. So the smaller ones is like, yeah, it's just there. But this is the part that's like mainly participating in the bonding. Am I audible to you guys? Yeah, okay.
Yes, ma'am.
Yes.
Cool. Abhi, I just got a message that my internet was unstable, so I just wanted to clarify. Okay. All right. So here's an example. The example given here is formation of BeCl2, beryllium chloride. So electronic configuration of Be is 1s2, 2s2, 2p1. Atomic number 4 hai. So ground state, excited state. So like 1s and this p orbital are taking part in the bonding. So either promotion has happened, but in general for hybridization, this is like not a necessary condition. So sometimes it is expressed in this way so that it makes it easier to figure out कि hybridization में कितने orbitals जाना चाहिए. So you just take all of the unpaired electrons, distribute them equally in the orbitals, and then you get an idea. Okay, so in सारे electrons को pair up करना चाहिए, then all of these orbitals needs to go into hybridization. That way it's easy to figure out. Yeah. So the 2s and one of the 2p orbitals hybridize to form 2sp hybrid orbitals. So यहाँ पे इसका 2s orbital and one of this 2p orbitals pz combine, they form sp hybrid orbitals. So hybridization के बाद the 1s2 remains as it is. You have the two sp orbitals. So this is 1s2, which is unchanged. You've got the sp hybrid orbitals, and this remaining 2px and 2py orbitals remain unchanged. Okay. So you've got unpaired electrons in the sp hybrid orbitals. So these are the ones that participate in bonding. So they overlap with the half-filled 3p orbitals of chlorine atoms. So again, chlorine का electronic configuration. So chlorine का electronic configuration क्या है? 1s2, then 2s2,
2p3.
huh?
Can you can take
Okay,
neon
wait. 2p, 1s2, 2s2, 2p6,
2p6, 3s2,
3p5.
17, right? 3p5.
3p5. So unpaired electron 3p orbital में है, and it's only in one of the 3p orbitals. So only this orbital alone needs to take part in the bonding so that this electron can get paired up. So that's why the sp orbitals overlap with the half-filled 3p orbitals of the chlorine atoms, and because they are overlapping on the same internuclear axis itself, what kind of overlap would this be?
Sigma.
Sigma overlap.
Sigma.
Yes, to form sigma bonds. Okay, so you've got beryllium. So you can see here बहुत ही lightly printed है ये sp orbitals का opposite like the other part. So anyway, these are the two sp orbitals and these are the chlorine k p orbital. So this is how you represent the bond. So it's written here, right? So sigma, showing that this is a sigma overlap between sp and p. Not sure how visible this is, but this is how it's written, sigma spp. Okay, indicates it's a sigma overlap between this and this. Cool. Can you guys do one on your own? sp hybridization, right? Can you guys do the formation of ethyne? अच्छा, example 2 इधर ही गया है. Okay. Can you show what is the overlap in ethyne? What kind of bonds are formed and send it? Just draw it in your books and send it on the group.
Ma'am, we have to do example 2 or ethyne.
Ethyne. दोनों में
Okay,
difference क्या है?
example 2.
Yeah.
I thought we had to do ethene.
Ma'am,
Yeah.
so for hybridization, you only take the excited state of the central atom or like the other atoms as well? Because like
Central atom.
here
Because
carbon.
carbon ठीक है. So carbon is bonding with hydrogen, right? So hydrogen में कितने electrons are to be bonded?
One.
One. So do you think any hybridization is required in that case?
I mean, when I look at like ethyne, I just think of the normal formula, the structural
Line
formula.
this thing, right?
Yeah, I'll try.
Just try it out and then I'll do it on the whiteboard.
Done, ma'am.
Done. Vidya?
Acha, you have to say.
Okay, you sent the electronic configuration. हाँ तो स्ट्रक्चर कैसे होगा? ठीक है, sp बन रहा है, but how is the molecule getting formed sp orbitals के
I
साथ?
have to draw also.
Yeah. So I guess working on it, or should I do it here?
Ma'am, can you check?
Okay. H C2H H2
Because
na,
I've got
but you have
two.
three hydrogen I can see three hydrogen atoms here.
Ma'am, sorry, the one is in that mess, the scratch thing. Sorry.
अच्छा,
Yeah.
नहीं लेकिन
But
C2H2 है ना, तो फिर C2H4 कैसे बन गया?
sorry.
Ethyne.
Sorry.
Okay. Ishita, Taranum, Sid.
Ma'am, just a minute.
Okay, you're doing it.
Just show it. I'm not getting it.
Not getting it? ठीक है, I'll do it here.
Ma'am, so in my thing, if I remove the sideline wala thing, then it's done, right? What happened?
Not exactly. You got like, I think I'd say about 30 to 40% correct. It's almost there. Anyway. Okay, so C2H2 ethyne. ठीक है. So you can take hints from the structural formula, okay? So you know that it's supposed to be C triple bond C bonded to 1H, right? Okay, just keep this aside abhi ke liye. All right. So the central atoms are carbon. दो carbon atoms है. And abhi bada hint, like we're doing it in context of sp hybridization. All right. Let's start off with carbon ka electronic configuration. 1s2, 2s2, 2p2. यहाँ तक you guys are aware. So s is paired, p orbital में both of these are over here. ठीक है. So अभी क्या हो रहा है ना? Now in this case, this particular carbon is bonded to how many other atoms?
2.
2. So it is bonded to, so it's bonded to this hydrogen here and it's bonded to this other carbon over here, which means that this carbon has to, it needs two orbitals that it can, like two hybrid orbitals to bond on either side. Similarly, the other carbon atom also has bonded with one on hydrogen and the other with the other carbon itself. So this also needs two hybrid orbitals so that it can bond on either side. So two hybrid orbitals चाहिए मतलब it needs to undergo sp hybridization. So इसमें excitation is required in this case because it is bonding with two other atoms, and apart from that it's forming a triple bond, which means that there's two additional atoms here. So if there's already, like if it forms a, if this s and p atomic orbital takes part in bonding, there's a total of 3 electrons, but I will need only 2 electrons right now in hybridization because the two sp orbitals are to bond with the two other atoms. So we've got ground state and we've got excited state, so that all the electrons are unpaired. So 2s may there's single, in the 2p orbitals there's one each. So now the one s orbital and one p orbital can combine to form two sp orbitals. So after hybridization, you've got 1s2 paired electrons, then two of these sp hybrid orbitals with an unpaired electron in each, and then the other two p orbitals will remain as it is. So you've got 2px and 2py. So now the first carbon, this particular carbon, iska sp orbitals are arranged linearly. The other carbon atom also needs sp hybridization, तो उसका भी the sp hybridized orbitals are arranged linearly. Now this is also bonded to one hydrogen, and hydrogen का एक ही electron है, so that's like 1s of hydrogen के साथ overlap है, and then ये carbon भी 1s of this other hydrogen के साथ sigma overlap है. Now all of them are in the same axis, so this is one sigma bond between sp and s, this is another sigma bond between sp and s, and this particular overlap is a sigma bond between sp and sp. ठीक है, यहाँ तक ठीक है? All of you have got it, like whoever has sent in the images. All right, तो इसको काउंट कर, ये तो this is not taking part at all. इसको काउंट किया हमने, इसको काउंट किया हमने. दोनों हाइड्रोजन भी हो गए. Now we've got these two unpaired electron. Now how are these shared with each other? So these particular p orbitals, they are still existing in these carbons itself, and they are again at right angles to each other. Like let's say 2px is in green, and I'll put 2py in, abhi kaun sa color bacha hai, maroon. So this is again perpendicular, आगे पीछे जा रहा है ऐसे. ठीक है. So these, again, there's one unpaired electron in the green 2px orbital, and there's one unpaired electron in the py orbital. Now these will basically combine with each other to form your pi bonds. Okay.
Ma'am, how did 2pz come into picture?
Yes. Huh?
How did 2pz come into picture?
2pz has gone in, like that took part in hybridization. So we're left with 2px and 2py.
No, because from what I did, I got like two p orbitals, like one above and one below. So I thought like that.
So that's what, like, I think your logic or your intent is correct, representation is wrong. So p orbital ka shape itself is dumbbell shape. Like both these lobes together make one p orbital. So either px or py or whichever. So if you have two p orbitals, like two different p orbitals, they are aligned perpendicular to each other.
Okay. So
So remember our pi bonds जो p orbitals के बीच में होते हैं, like यहाँ पे एक ऊपर एक saucer shaped होता है, and then imagine screen के आगे और screen के पीछे यहाँ पे दो और clouds है. So this is one of the p orbitals forming bonds, and axis के ऊपर नीचे, this is the other p orbital forming the pi bonds.
okay.
Ma'am, can we do like more of these drawing type of questions?
Yeah, we'll do that. So multiple different types of hybridization hai na. So this is when it comes to sp hybridization. So pehla example tha, that is just a very simple case where you just had beryllium taking part in bonding, and it only had like two electrons to pair up, straightforward ho gaya tha. In this case, this is a slightly more complicated than the previous thing. So isme you're coming across both your sigma overlap that is happening between these orbitals and also the pi overlap. Okay. And this is how your triple bond comes into question. So your sigma overlap is the first bond जो CH, CC and CH के बीच में हो रहा है. Then one pi overlap, like इसका 2px और इसका 2px में जो हो रहा है, that is this second bond. And तीसरा pi overlap जो हो रहा है between the 2py of this and the 2py of this carbon atom, ये जो हो रहा है screen के आगे पीछे, so this is your third bond. Okay, so that's how the triple bond of carbon is, like between these two carbon atoms is.
How do you figure out how many hybridized orbitals are there?
So for that, check how many different atoms, or how many, like figure out what electron geometry is required. So when you go back to VSEPR, this carbon is bonding with this hydrogen and then this other carbon atom. So VSEPR mein, if you recall, even though there are multiple bonds, double or triple, it is considered as like one super bond, right? And apart from these two bonds, there is no other lone pairs or anything else that this carbon has, which means that it needs orbitals, like it basically needs two hybrid orbitals aligned in like opposite directions. So if you want two hybrid orbitals, you need to give in two atomic orbitals, because how many ever atomic orbitals you take, those many hybrid orbitals get produced. So if you want two hybrid orbitals, two atomic orbitals, matlab, it is going to be sp hybridization. So I'll take another example. So the next type of hybridization is sp2 hybridization. I'll discuss sp2 and then I'll compare both, तो उससे और थोड़ा clarity आ जाएगा.
Can we do one more SP before
One more
going
sp.
SP?
Okay, one moment. So I'll see if there's another simple one that I can see that can be done with sp hybridization. Okay, do it for कार्बन डाइऑक्साइड. हाँ, उसका शेप भी लीनियर है ना. हाँ, do it for CO2. Share the whiteboard. So again, कार्बन के केस में we've got 1s2, 2s2, 2p2. ऑक्सीजन के केस में you've got 1s2, 2s2, 2p4. In this case, oxygen is forming a bond with only one other molecule, which happens to be carbon. So oxygen के case में hybridization is not required. So only carbon के this ring will undergo hybridization.
Ma'am, why not oxygen?
Because oxygen is only it is bonding only with carbon, right? It is like, if you look at it from oxygen's point of view, okay, this is the structure, right? This particular oxygen is bonding only with carbon. It doesn't, there is no need for this particular oxygen to like maximize or minimize repulsions or anything like that.
Okay.
इसलिए. But in the case of carbon, it is bonding to two other atoms. So इसमें this one is required to, you know, arrange so that both of them are at maximum distance from each other and everything. इसलिए.
Ma'am, so what I drew is I took a carbon atom,
Yeah.
then I drew 2p, 2px, 2py, 2pz, all three of them.
Mm-hmm.
And because if I look at oxygen's electronic configuration, the two orbitals that are going to take part in the orbital
The
diagram or the bonding is 2py and 2pz, correct?
two of the orbitals, yeah, x, y,
Yeah,
or y, z, whichever.
yeah, 2py, 2pz. I'm going in the order only. So, in the 2px thing, I made one orbital here. So, like, mm, how do I explain? So, I made a infinity, the carbon thing. Okay,
Uh-huh.
then I took on the same axis. I drew two p orbitals as well simultaneously on this side
ठीक
and
है,
this side as well.
correct.
But then now I don't know what how to go further. Like
Okay,
which of the orbitals should I take
the
for that?
second one, right?
Yeah, yeah.
Hmm. Okay, so the pi bonding part you are confused with. So agar one bond is always sigma bond, the first bond is always sigma bond, and whichever additional bonds are formed, the double bond may the second, या triple bond है तो the second and third, they are all pi bonding. ठीक है. Okay, any, like, who else is working on it?
Ma'am,
Hmm.
I have written the excited state of carbon, but
Okay.
after that, how do I begin with the structure?
कितने हाइब्रिड ऑर्बिटल्स फॉर्म होना चाहिए?
Hybrid orbitals.
कितने
क्या
चाहिए
मतलब है
हमको?
इसका?
Like how many hybrid orbitals do we need bonding के लिए? How many और hybrid orbitals does carbon need bonding के लिए?
2.
Two.
No, it
मतलब
needs 4, but it can only get 2.
नहीं, it has all four available. एक S है, तीन P है. It needs only two because it is bonding with only two. So this is one and this is the other. Okay, so it needs two. Like if you had methane where carbon is bonding with four hydrogens, इसमें it is forming four different bonds, तो इसलिए in this case it needs four hybrid orbitals. But in this case carbon dioxide में carbon is bonding with oxygen number 1 and oxygen number 2 और इसके पास कोई lone pairs भी नहीं है. So इसके geometry में there's only two electron pairs that it is like it has. These are double bonds, it's a different matter, but there's like two major bondings that's taking place here. Okay, so that's why
Yes.
it needs two hybrid orbitals. All right, so two hybrid orbitals matlab one s and one p. After hybridization, one s2 वैसे ही रहेगा, and then you've got the two sp orbitals, and the remaining two 2p orbitals will remain as it is. So 2px, 2py मान लो. All of them with their single electron. Oxygen is going to remain as it is. So this is what the structure is going to look like. So sp orbitals ka shape is going to be linear. So this is the carbon. So carbon के दो sp orbitals है. This is going to overlap with the pz orbital of oxygen, the 2pz. So pz is a pure proper orbital, तो उसका shape होगा in the dumbbell shape, normal p orbital. Same with the other oxygen's p orbital. Now because all of it is in the same axis, this is going to be a two different sigma overlaps. So this is sigma spp, this is sigma spp. Now, this is the sp orbital taken care of. Apart from that, we have a px में unpaired electron and कौन सा color? Green py में unpaired electron. Now both of these are going to be in perpendicular. So if this is the z axis, x and y are going to be perpendicular to each other. So if x is perpendicular in this direction, the py is going to be aligned in this direction. Like screen के आगे पीछे मान लो. ठीक है. Now oxygen के case में भी only one electron was paired, z axis में जो भी है, from the sigma overlap. Now each of this oxygen has, like oxygen number 1 has py का unpaired electron, and then CO2 है ना, so the second oxygen also has the py में unpaired electron. So this is oxygen number 1 and this is oxygen number 2, maybe 2s2. So px, py, pz. So pz ये overlap से this has been satisfied. Now this unpaired electron is there. Now the oxygen atoms each will be over, they will align themselves such that इसका एक p orbital will form a pi bond with the 2px of carbon and इसका दूसरा this orbital will form a pi bond with the 2py of carbon. ऐसे. Okay. So this is pi pp, of course, p orbital and p orbital, and this is the other pi pp orbital. So if you look at the double bonds, the double bond with one oxygen is ये वाला, like one of the p orbitals of carbon, and the double bond with the second this particular pi bond is this one, the second bond with the other oxygen. So the overall geometry is linear because all of them are in a same straight line. Now these pi bonds are parallel to the already present sigma bonds that are here. So let me take a highlighter. Yeah. So this is one sigma bond. So this pi bond, which is there both above and below, is parallel to the sigma bond. And this other one, this is the second sigma bond, which is in the same straight line on the opposite direction. Ye wala pi bond is parallel to this axis. This is behind the screen and this is in front of the screen. Okay. Ansh has already sent it. Nice. Good stuff, Ansh. This exactly, you got it. So sigma है, ऊपर और नीचे दोनों pi bonds है. Sid sent it, sorry. Ansh, what happened? Good afternoon, Ansh. What happened?
Hello.
Yeah, now I can hear you.
I didn't know the class today, that's why.
Oh, didn't check the schedule. ठीक है. Okay, so we were discussing hybridization. तो अभी SP खत्म हुआ. We'll be starting SP2, SP3 next. Anyway, this is recorded, so I'll just post it in about 2-3 hours after the class. You can refer to it. Okay. So abhi, like, is it like how these pi bonds are formed? Are you clear with this now? ठीक है?
Yes, ma'am.
Yeah. So same thing happened in the case of ethyne also, just that both of these pi bonds happened between the same carbon atoms. So उस case में both the p orbitals were forming the pi bonds with different oxygen atoms. In this case, these pi bonds formed with the same carbon atom. So in all directions, you've got bonds. So एक axis पे you've got the sigma bond, and then x axis पे you've got one pi bond, and y axis पे you've got the other pi bond.
Ma'am,
Yeah.
you had said that for methane, carbon will have 4 hybridized orbitals. I didn't get that part. How can I have 4? Shouldn't I only have 2?
We'll discuss that. ठीक है? So we'll do sp2 also, and then उसके बाद sp3 also. So we'll take all of these cases, तो उससे थोड़ा clarity मिल जाएगा. Okay. Cool. So this is sp hybridization. Next comes sp2 hybridization. So basic important points about sp2, you can use common sense logic and figure it out. So what all atomic orbitals will it take to produce sp2 hybrid?
One s orbital, two p orbitals.
Absolutely. So one s orbital and two p orbitals. I'm writing 1 and 2 in this because I don't want you guys to get confused with the 1s, 2s, 2p, all of that. Yeah. So a single s orbital and two of the p orbitals combine to form. How many sp2 hybrid orbitals will there exist when this happens?
3.
Yes. So the total of 3 atomic orbitals are taking part. So you will get 3 sp2 hybrid orbitals. So if there are 3 sp2 hybrid orbitals, how will they be aligned? Shape क्या होगा? So if you have 3 orbitals, कैसे align हों? Like how will they be aligned to maximize or minimize repulsion? Yes, sir, you were saying?
No, I'm getting confused in the question. I don't understand what the question is.
So I've got 3 of these sp2 hybrid orbitals. How will you arrange 3 orbitals to minimize the repulsion between them? So when I had 2 hybrid orbitals, the only way I could minimize the repulsion is by aligning them opposite to each other at 180 degrees. तो उसका shape like sp2 का shape linear हो गया. So that way in this case, I've got 3 sp2 hybrid. So how will I align all 3 sp2 hybrid orbitals to minimize the repulsions? Like imagine it. Yes, Mitali has answered. Good stuff. So nucleus है. इसके around I've got 3 of these sp2 hybrids. So how will I arrange all these 3 around this nucleus to basically maximize the distance between them? Go back to VSEPR. Trigonal planar.
180 degrees to each other.
हाँ 180 कैसे?
अरे
3 है ना?
120.
हाँ 120 with each other. Yes. So ये कौन सा shape है? If you look at it. So all 3 of them, when you get 3 sp2 hybrid orbitals, they are all aligned at 120 degrees from each other and they form a trigonal planar shape. ठीक है? You can connect this with VSEPR guys, like VSEPR पे build कर रहे हम. So VSEPR में when we had 3 electron pairs, like 3 bond pairs या 1 lone pair, 2 bond pairs जो भी है, उनको कैसे arrange किया in order to minimize the repulsion? Trigonal planar में arrange किया ना? So similarly here also you've got 3 of these hybrid orbitals. Just because we call it hybrid orbitals doesn't mean it's a new thing. Hybrid orbitals also contain electrons only. The special thing about hybrid orbitals is that these are the specialized orbitals used for bonding. So obviously bond pairs hybrid orbitals में ही रहेंगे. ठीक है. Still blank or like did it click? Yes, Mayas?
It clicked,
Yes,
but I'm not able to visualize it in the board.
Oh, see. So again, like you've got 3 hybrid orbitals. If you had to arrange all 3 of them, they arrange themselves in trigonal planar. So bond में कैसे करेगा? Like I'll give you an example. Like example लेके we'll see how the bonding is. Okay. और क्या shape we discussed, how it is formed we discussed. What would be the percentage of S character and P character in this?
33%, 33.33.
किसका?
Sorry, P का.
P का कितना?
गलत बोला मैंने.
33.
किसका
S का
33?
33.
हाँ.
S का.
You said 33.33. I didn't catch S या P. Okay, तो फिर P का कितना character? 60.
नहीं पता नहीं.
Should be 66, right?
66.67.
Yeah, you don't have to be so doubtful, guys. 3 orbitals है. 1/3 of it is S, 2/3 of it is P. उसको percentage में convert कर लो, मिल जाएगा. It is as straightforward as that. Okay.
Yes.
Okay.
ठीक है. Yeah, these are the basic characters. और कुछ है discuss करने के लिए? Geometry, S character, and how many and what. ठीक है. All of that is done. So now all we have to do is do it with the help of an example. किधर गया whiteboard? There it is. हाँ. So one of the common examples you take, a straightforward example is boron trichloride, BCl3. ठीक है. So बोरॉन का इलेक्ट्रॉनिक कॉन्फ़िगरेशन क्या है इसमें? बोरॉन इज atomic 5.
You take organ core.
S2P1.
Ma'am, you're going to write the thing?
No, boron is 5. Atomic number is 5.
Boron. Oh, sorry.
1s2, 2s2, 2p1.
1s2, 2s2, 3p1. And so 3, 2p1. 2 होना चाहिए, sorry. So valence shell में there are 3 electrons and all 3 of them are bonded to chlorine. So that means now because it needs to form 3 bonds, right? So boron hai, chlorine, chlorine, chlorine. There's no double bonds or anything there. So because it needs to form 3 bonds, that is why it needs 3 hybrid orbitals. So whenever you're trying to figure out, so basically it's this way. So first check how many electron pairs are there around the central atom. So in the previous example, if you take BeCl2, iska structure tha Be was there, Cl was here, Cl was here. Or even for that case, carbon dioxide, all of these were linear. So carbon ke around, there were no lone pairs. It just had like two bonds forming with 2 different atoms. Same is the case with beryllium also, just 2 bond pairs, 0 lone pairs. So that is why, because it had to bond with 2 separate atoms, it needed space to keep 2 electron pairs. That is the reason it needed 2 hybrid orbitals. And how do you get 2 hybrid orbitals? By taking 2 individual atomic orbitals. So that way, around boron, it needs space for 3 bond pairs. There are no lone pairs at all. So 3 bond pairs के लिए space बनाना है, मतलब it needs 3 hybrid orbitals. And अगर 3 hybrid orbitals चाहिए, then I need to take 3 individual atomic orbitals. That is how you get sp2 hybridization. Because you take 3 atomic orbitals, 1 s and 2 p orbitals, you get 3 sp2 hybrid orbitals. Then it can arrange the 3 orbitals so that, you know, all of them can bond with chlorine. So you can basically reverse engineer it in that way. Okay. So now boron needs to form 3 different bonds with each of these chlorines. That is the reason it will undergo sp2 hybridization. Okay. Ground state में it's got 2s and 1p. Hybridization के बाद so 1s2 will remain as it is. This particular s orbital and one of the sp2 है ना, so 2 of these p orbitals will combine to form 3 of this sp2 hybrid orbitals. And then this remaining p orbital will remain as it is. So each of these electrons are again distributed in these sp2 hybrid orbitals. Now sp2 ka distribution, we know that it's in trigonal planar form. 3 orbitals hai na, and if you had to symmetrically distribute them, you need to put them in trigonal planar form, equal angles with each other. So these are the 3 sp2 hybrid orbitals, and each of these is bonding with a chlorine atom. So which orbital of chlorine will overlap with this? So chlorine का unpaired electron कहाँ पे होगा?
PZ.
PZ. So इसका p orbital is going to overlap इसे. So this is boron and each of this is chlorine. So this is what kind of overlap, if I have to name it? Sigma. And what kind
Yes.
of sigma?
P2 with PZ.
Yeah, sp2p. This one?
It will be the
Same
same
thing.
for everything, right?
Yes.
sp2p, sp2p.
Correct. Sigma sp2p. That's all. So this is basically the structure of boron trichloride. So whichever molecule, as long as you see that it is forming 3, so as long as it has 3 electron pairs. 3 electron pairs matlab either 3 bond pairs or 2 bond pairs plus 1 lone pair. As long as this is the case, it will undergo sp2 hybridization. The reason is that it's got 3 electron pairs, right? Be it bond pairs or lone pairs. Now it needs, like this atom needs space to arrange these 3 electron pairs so that the repulsion between them is minimum. Stably arranged karna padega. And that will happen, like if it does not undergo hybridization, बहुत ही सारा hodgepodge हो जाएगा. Like s orbital is spherical, फिर p का dumbbell is arranged something like this. If it were to form a sigma bond with this, फिर s is like inaccessible. So बहुत ही hodgepodge हो रहा है. So that is the reason ये सारे पूरा, like they all combine and then form stable hybrid orbitals so that all the electrons are happy. No one is getting in each other's space. ठीक है. So again, sp जैसे डिस्कस किया था, this is straightforward sigma bond के साथ. Will you guys be able to do pi bond के साथ? So if I were to ask you to draw the hybrid orbitals and structure of ethene, C2H4, will you be able to figure this out? कैसे रहेगा ये? So if you look at ethene structure, C double bond C, H, 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 H. So just drawing the structure like this itself is a big hint. So say you should be able to figure out.
Now, ma'am, so now I'm looking at the structure, okay? And you said firstly consider how many electron pairs are there. So like 1, 2, 3, 4, 5, 6.
Again, there are two different carbon atoms, right? Take one carbon at a time. So if I'm considering this particular carbon, तो ये हाइड्रोजन के साथ एक बॉन्ड हो रहा है,
Correct.
ये वाला हाइड्रोजन के साथ एक बॉन्ड हो रहा है. नाउ इस वाले कार्बन के साथ देयर इज अ डबल बॉन्ड, but it's the same carbon atom. So consider this as like the another space that this carbon needs to give to this carbon. See,
this one will be sp4. No, sp3, sorry.
Again, just because it's a double bond, don't consider it as two different electron pairs, because these two are not going to repel each other. It's a double bond. So all of them are shared between these two carbon atoms. Again, go back to VSEPR theory where it says if you have double or triple bonds, consider it as a single supersized bond. And another factor is that every time you have a double or triple bond, you can take it for granted that it has one sigma and any additional bond is a pi bond. So double bond में you have one sigma and one pi bond, and triple bond में you have one sigma and two pi bonds. So pi bonds hybridization में, like hybrid orbitals में you don't really come across pi bonds. That always happens with p orbitals because it's not along the nuclear axis. एंड इस कार्बन पे कोई और लोन पेयर भी नहीं है, सो इट्स अ टोटल ऑफ 3 spaces that this needs to give for bonding. You guys had done organic chemistry, na? So all this would have been revised again there.
No, ma'am, the only questions we actually did was not including structures, only simply writing hybridization, like sp for alkanes, sp2 for alkenes, sp3 for.
उल्टा बोला.
हाँ, sorry. Yeah.
अच्छा, स्ट्रक्चर नहीं करवाया. ओके. Ansh, how are you with hybridization? Like you joined in the middle, right? Are you able to follow? अगर कुछ question है तो पूछो.
I'm not totally confused, but it's fine. I'm able to follow.
Okay, cool. Okay. So carbon again electronic configuration पता है. 1s2, 2s2, 2p2. अभी 3 है, मतलब like you can guess कि 3 sp2 होगा because we'll need 3 hybrid orbitals. So again the same things. इसको एक्साइट करना पड़ेगा because एक pi bond है, तो उसके लिए 1 electron needs to be in the extra p orbital. So this is ground. Excited state में Then hybridization करने के बाद 1s2 will remain untouched. फिर I get 3 of these sp2 orbitals, and this p orbital will remain as it is. sp2, 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 and then this is a 2p orbital. Cool. And hydrogen, yeah.
In this question, why don't we create sp3, because we have 4 hydrogen to
4 hydrogen, लेकिन that's why focus on one carbon at a time. दोनों combined form नहीं कर रहे हैं ना, दो अलग अलग कार्बन एटम है ना. So if you look at this carbon, it is forming 3 bonds, एक हाइड्रोजन, दूसरा हाइड्रोजन, and तीसरा ये कार्बन के साथ. Similarly, if you consider the second hydrogen, it's forming 1, 2 and 3 with this carbon. So individually हर एक carbon, this is also forming, this has 3 electron pairs, this is also having 3 electron pairs. मतलब like 4 electron pairs, but एक तो double bond हो गया ना. So basically like 3, like what do you call it, bonding spaces, like it's forming 3 different bonds. Yeah. Now because 3 है तो 3 hybrid orbital चाहिए इसके लिए. So पहला कार्बन, दूसरा कार्बन का, so ये इसका एक सिग्मा बॉन्ड we have taken care of, this is that. Then of course यहाँ पे सिग्मा बॉन्ड हो रहा है हाइड्रोजन के साथ, and हाइड्रोजन का configuration is 1s1. s orbital is spherical, so that is going to be like this, s orbital. Same with this side, इन दोनों हाइड्रोजन्स के साथ भी. So this is hydrogen, this is hydrogen, this is hydrogen, this is hydrogen, and these are the 2 carbons. So all these so far are sigma overlaps, क्योंकि direct like nuclear axis पे ही हो रहा है. So this will be what kind of sigma? Sigma
sp2
sp2.
s.
only sp2. क्या क्या participate कर रहे हैं इसमें?
sp2s.
sp2s.
S, yeah, sp2s. So this is also sigma sp2s, sigma sp2s, sigma sp2s, and the central one is going to be sigma
sp2 sp2
sp2 sp2. Naming
Ma'am,
is
here
just figure out what, huh?
oh sorry, here we follow the VCPR postulate that 2 double bonds are considered one super
Yeah,
bond, right?
yeah.
Okay.
So that's what you used to figure out कि कितने hybrid orbitals चाहिए. And the reason for doing that is the double bond, like double bond or triple bond के case में, the first bond is a sigma bond, which is what you're considering for hybridization, and every extra bond that is there, the orange parts, are going to be pi bonds only. So pi bonds, because they are perpendicular to the nuclear axis, usme you don't like, that is undertaken by p orbitals mainly.
Okay.
So hybrid orbitals don't really take part in your double and triple bonds, like the first, or rather the pi bonds. So double triple bonds may only the sigma bond is undertaken by the hybrid orbital, which is why we considered it as one bond, second bond, triple, third bond, इसलिए three hybrid orbitals चाहिए. So that's how we considered it.
So, ma'am, can I say, sorry, can I say
yeah,
that SP2 only, because during SP3, right? Yeah.
SP
So,
discuss किया था.
oh, sorry. So, during SP hybridization, because there are no double bonds as such, like even if they are, we show the pi bonds, right? And during sp2 hybridization we consider it a
No,
single
we are
super.
showing, we are going to show the pi bond. So that's like the next step.
Okay.
ठीक है?
Sorry,
हाँ.
I thought that it's over.
नहीं नहीं. So that's what I was drawing a parallel. अभी double bond में the second bond was a pi bond. So only one bond we considered, इसलिए three orbitals आए हैं. So if I look at it in sp ethyne के केस में, so we've got C triple bond C. तो इसमें again here also we considered that carbon is being bonded only to two other atoms, एक hydrogen के साथ, एक दूसरा carbon के साथ. So ये दूसरा carbon के साथ, even though there's a triple bond, we only considered the first sigma bond which will participate, like in which the hybrid orbital is participating, because the other two, these two that are there, are basically your pi bonds, ऊपर और side में. Similarly, even in this case, only one bond is considered for sigma, the other one is going to be considered for pi bond. So that's how is the pi bond going to look like. So that pi bond is going to be aligned perpendicular to the plane in which this particular trigonal planar is there. Okay, so it's going to be, so अगर ये, if this is like flat on the screen पे ऐसा है, एक ही plane पे है, तो your pi bond is going to be perpendicular. So imagine screen के आगे पीछे जा रहा है. So that's where your pi bond is formed. So I'll just switch on my video. So the trigonal planar, the way you look at it here, can you guys see me?
Yes, ma'am.
So let's say the trigonal planar is like on my hand ऐसे. Okay. So the pi bond is basically, if this was the plane, like I just rotated my hand here, इस पे flat है, your both the carbon atoms and the four hydrogen atoms. The double bond that you have, which is basically the pi bond, is going to be perpendicular ऐसे. So ऊपर की तरफ एक pi bond होगा, नीचे की तरफ ऐसे एक pi bond होगा. It is perpendicular to the plane in which the carbon atoms are there. So if the carbon atoms are there in the plane of my hand, the pi bond is going to be above and below my hand. Okay, so if you look at it, it's going to be perpendicular, आगे और पीछे. So the pi bond में you have the two saucers, right? So one saucer is going to be यहाँ पे ऊपर, and the other saucer is going to be नीचे, पीछे. Does it make sense? Click हो रहा है?
Yeah.
See, like if I get a 3D visual simulation sort of a thing, I can do this. Sid has gotten it. This is also right. He's mentioned the pi bond also. Nice. Mitali has also sent in, yes. Mitali, one correction, whenever you indicate the pi bond, you need to indicate on both the sides, because dumbbell extends on both sides,
Okay.
right? Upar or niche. So the saucer is
So,
formed both sides.
okay, so I do that, and on both the sides
Yeah.
I say pi.
Yeah.
So that is if I actually do that. But I thought that was wrong.
No, you
Isn't
were
it wrong?
actually right. वही किया ना, like you had the trigonal planar and
Yeah, but it's messy. Okay.
हाँ थोड़ा like I can see sigma overlap है, दो हाइड्रोजन के साथ sigma overlap है. So basically you tried to portray uh, like the two hydrogen ka is like behind the screen and
Yeah.
in front of the screen, right? Yeah, I got that. So in that case, the pi bond is going to be ऊपर नीचे both ऐसे.
Okay. So yeah. Okay.
Hmm.
I got it.
Yeah. Cool. All right. Sid has gotten it. Mitali's gotten it. Mayas, Ansh, Ishita, Taranum. What about you guys? Making sense?
I have
आ रहा
also
है?
done, but I did not send.
Okay. ठीक है. But understood, like, is it making sense? आया?
Yes, sir.
Okay.
Yeah, I got it now.
Better? ठीक है. Cool. And then finally, sp3 hybridization. Again, फटाफट sp3 में what all atomic orbitals will take part?
Ma'am, can you give an example? So
1s 3p.
नहीं, sp3 का like basic we'll understand what the orbital is और उसके बाद examples लेते हैं.
1s orbital and 3p orbital.
Yes.
Oh, that sorry.
1s and the 3p orbitals. Next, percentage s character कितना है इसमें and percentage p character कितना है?
S25 75 p.
Yes. Then okay. Total कितने sp3 form करेंगे? So if we combine 1s and 3p.
4.
Yes. So you get 4 sp3 hybrid orbitals. So if I have 4 of these hybrid orbitals, what is the shape that they will take? Imagine arranging 4 bond pairs. What?
Tetrahedral.
Tetrahedral. See, now you guys got it. Yes. ठीक है. So sp3 hybrid orbitals के लिए you have a lot of examples, different cases again. So essentially wherever you have 4 different electron pairs, all of them will come under sp3. The most common example, first one is methane. So Sid, you were asking, right, like methane, why sp3, why not in the case of ethane or any other things? So if you look at the structure of methane, you have carbon bonded to 4 different hydrogens. Now, does it have any lone pairs?
No.
No. So how many total space does this carbon need to create so that all of these bond pairs are like happy, no repulsions?
4.
4. Now, because it needs to create 4 of these spaces, how many hybrid orbitals are required?
4.
4. Yes. So 4 hybrid orbitals are required, matlab. That is why methane is going to undergo sp3 hybridization. Okay. So now this is pretty easy. So you guys draw the structure of methane. 2 minutes में draw कर लो. I'll need to keep my laptop for charging. I'll be right back. This time I want to see answers from Ishita, Ansh and Taranum also. Draw करके send the picture on the group.
Ma'am, actually my phone battery died. So.
अरे okay, तो एक काम करना. So once the class is done, whatever notes you've made, just click a picture, like make the PDF out of it, and then you can send it on the WhatsApp. Either send it on WhatsApp or you can upload it on the classwork submission link. Mitali, yeah, it can get messy because tetrahedral ना 2D में अगर दिखाना है तो थोड़ा अजीब ही लिखेगा.
My thing looks like a flower. I'm not even kidding. So
Maya's
is
थोड़ा
it visible or I send it on
no.
WhatsApp? Okay.
हाँ थोड़ा सा left. Yes.
But
Yes.
in
Correct.
that case, you only draw one thing, right? You have to draw like both the.
So the other one is छोटा enough that you know it's late. It'll be barely visible. तो ऐसे इतना draw कर सकते हो चलेगा.
Acha, because I drew that also. That's how it's looking very.
हाँ. Because if you
तो
draw
ignore
them
कर सकते हैं
equal,
शायद.
वो तो it's like it's as equal to a p orbital, but in fact it's not. So yes, Ishita has also got it. Nice. So carbon के around वो circle draw करने की जरूरत नहीं Ishita. You can just like have the 4 hybrid orbitals ऐसे ही. तीसरा इधर और fourth one will be at the back, थोड़ा पीछे की तरफ. You made it correct only Ishita. It looks like a tetrahedron, just that center में circle जो draw किया ना, so that is not required.
Yes, ma'am. Ma'am, I just directly did it with a pen. I don't usually use a pen for drawing.
Ah. And overlap थोड़ा ठीक से दिखाना पड़ेगा. One of the hydrogens. अच्छा, हर एक hydrogen का अच्छा you again that only like you don't have to put it separately. The circle itself represents hydrogen का orbital ऐसे. So you don't have to put another circle here. That would be wrong. So direct either you can either write it outside or within the circle essay you can put hydrogen.
Okay, ma'am.
Yeah. Awesome. Sid has also sent it. Cool. Got it. H and H. So this is carbon. Each of this is hydrogen. And हर एक case में you have sigma overlap. Oh, it's already 4:43. हमें molecular orbital theory भी करना था यार. We'll get really delayed. Okay. ठीक है. So this is methane. आसान है. Okay, हो गया. All right. Now let's do some freestyling. Our favorite water molecule. So water molecule में what hybridization do you think should be there? So obviously hybridization oxygen पे होगा because that's the central atom. So oxygen will undergo what hybridization to form water molecule?
SP.
SP. Are you sure?
SP. Because there are lone pairs as well, but I don't know how lone pair will play.
How many lone pairs are there?
2.
So total oxygen के around how many electron pairs are there?
SP2 then 4.
4, right? So 2 bond pairs plus 2 lone pairs. अभी इन 4 electron pairs को अच्छे से अगर if you want to arrange it around oxygen, how many orbitals will oxygen require?
Remember lone pair. Just a second.
Ma'am, is it SP3?
Yeah. So you have 4 electron pairs, no? सो एक लोन पेयर है, दूसरा लोन पेयर है, एक बॉन्ड पेयर है, दूसरा बॉन्ड पेयर है. सो यू हैव 2 bond pairs plus 2 lone pairs. मतलब oxygen needs to create space for 4 pairs of electrons. Because look at the alternative. So let's say, see, if it undergoes sp hybridization in दो bonds के लिए, these two will be linear to each other. sp, एक sp a से और दूसरा sp a से. ठीक है, these two are at maximum distance, but how will you arrange the other two lone pairs? So अगर वो p orbital में होना है, they'll be at 90 degrees. तो हर एक इलेक्ट्रॉन पेयर के बीच में एंगल is going to be 90 degrees. But if it undergoes sp3 hybridization, it's going to form a tetrahedral shape. So more angle. So electron pairs में repulsion है. So the farther they are, the more stable the atom will be, the more happier they'll be. So oxygen will prefer undergoing this sp3 hybridization so that it can get this tetrahedral shape, larger angle, like especially lone pair or bond pair के बीच में it's going to be almost like 109 degrees plus, 110, 112 degrees, as opposed to only 90 degrees if it does not undergo hybridization, right? So that is the reason it is preferable that water molecule में oxygen undergoes sp3 hybridization and uses
I do
these
not
two.
understand this.
Okay.
Like when I am given H2O, I start with writing the configuration of O first. Okay.
ठीक है, perfectly fine. Yes.
हाँ, तो आता है 1s2 2s2 2p4.
Yes.
तो वो बॉक्स से सुनाता हूँ मैं. तो 1s2 2s2 1s2 को इग्नोर किया, 2s2 एंड 2p4. फिर एक्साइटेड स्टेट में जाएंगे अभी.
एक्साइटेड स्टेट क्या, कहाँ, कैसे एक्साइट होगा इसमें?
S से एक इलेक्ट्रॉन p में जाएगा.
उससे क्या फर्क पड़ेगा?
वही तो समझ नहीं आ रहा अभी क्या करूँ इसके बाद.
सो इसमें एक्साइटेड स्टेट की जरूरत नहीं है. रिमेंबर, हाइब्रिडाइजेशन में इट्स नॉट नेसेसरी फॉर एक्साइटेशन टू टेक प्लेस. ऑल्सो सारे सिंगल बॉन्ड्स ही है ना, कोई पाई बॉन्ड्स तो नहीं बन रहा है. सो दैट्स लाइक नॉट अ प्रॉब्लम एट ऑल.
So after this, what is the next step?
तो अभी यू नीड टू डिसाइड कि किस तरह का हाइब्रिडाइजेशन होने वाला है इसमें. सो वन, डू यू थिंक हाइब्रिडाइजेशन इज रिक्वायर्ड? सो वही डिस्कस किया हमने. मिथाली, if you're saying something, I think you're muted. सुनाई नहीं दिया.
No, I mean, you just asked us that do you think hybridization is required in this?
Yeah.
So like, I mean, yeah. But
So,
is there like an easier way to figure out what kind of hybridization it is?
you just see how many electron pairs are there around the atom and then, yeah, decide. So यहाँ पे 4 electron pairs are there, 2 bond pairs plus 2 lone pairs. Yeah. So 4 electron pairs मतलब VSEPR से tetrahedral geometry. And basically 4 electron pairs matlab 4 different spaces to keep these atoms. So you need 4 orbitals.
Geometry is sp3 hybridization.
Yes.
That
so
we can remember.
Okay. Yeah. So if there are 4 electron pairs, if there are 4 bond pairs, if there are 3 bond pairs, array yaar, let me switch off video. Oh, my video is off. Anyway, so if there are 4 bond pairs or 3 bond pairs plus 1 lone pair, or if there are 2 bond pairs plus 2 lone pairs, whatever be the case, because there are 4 electron pairs, atom needs 4 spaces to keep those electron pairs, which is why all of this will come under sp3 hybridization. That's like a hard and fast rule that you can just like take for granted. ठीक है. So that is the reason water. And then the reasoning that I gave you, like if you take a look at both the cases, you know, a case where hybridization has taken place and a case where hybridization has not taken place. अगर hybridization नहीं हुआ, it means that overlap is taking with this particular p orbital and this particular p orbital. So in that case, both the bond pairs and lone pairs, everything is at an angle of 90 degrees with each other, because all p orbitals are at 90 degrees with each other. But if hybridization is taking place, tetrahedral shape mein, you're getting an angle of 109 degrees between each of these electron pairs. So electron pairs mein jitna, how, like the more farther they are, the more stable it will be, क्योंकि अगर distance ज़्यादा है तो repulsion minimum होगा. And that's what we are aiming at with all of these molecule geometries. So repulsion minimum hona chahiye. So that is why oxygen will prefer undergoing hybridization. Okay. Cool. Now can you draw what will be the shape of this particular thing?
Bent shape.
Bent, yes. So the hybrid orbitals will be in tetrahedral shape. एक इधर, एक इधर. So much of lag. एक इधर. And then the fourth one will be either आगे या पीछे से 109 degrees. ठीक है. So out of these, hydrogen will overlap with two of these. You can pick any two of them. And the other two are going to have individual lone pair of electrons. Okay. So that is basically the structure of water molecule. Okay. इसके basis पे, can you figure out what will be the structure of, like what is going to happen in ammonia? One, is it going to undergo hybridization? If yes, then what type of hybridization?
Tetrahedral only, right? Because like
Same
lone
as
pairs, bond pairs.
Yes.
Tetrahedral geometry,
Correct.
sp3.
So ammonia may you have one lone pair and three bond pairs. So that's also going to be tetrahedral. Water ke jaisi, except the third one also is going to have hydrogen, and this is going to be one lone pair over here. ठीक है. Cool. All right. So this is it about hybridization. These are like the main hybridization that you will come across. So all of these have involved s and p orbitals. So apart from that, you have other hybridization involving d orbitals also. I'll just quickly go over them. Okay. So sp3 कर लिया हमने. Formation of methane. So this is kind of the shape that you will come across, that you'll see here. Tetrahedral shape, methane ka structure. Then we've got ammonia also. Ethane also, everything is done. Huh. So next, involving d orbitals, you've got sp3 dehybridization. So this is when an atom needs to form like 5 different bonds. So a typical example is PCl5. So phosphorus is bonding with 5 different chlorine atoms. That means it's got 5 bond pairs. 5 bond pairs matlab 5 hybrid orbitals chahiye. So 5 hybrid orbitals ke liye, you need to put in 5 atomic orbitals. So you've got 1s plus 3p plus 1d orbital. all coming together to form 5 equivalent sp3d hybrid orbitals. So if you have 5 bond pairs, geometry क्या होगा?
Trigonal bipyramidal.
Yes, trigonal bipyramidal. So triangle in a plane और ऊपर और नीचे दो pyramids. ठीक है. Similarly, you've got sp3d2 hybridization. तो again sp3d2 मतलब टोटल कितने एटॉमिक ऑर्बिटल्स ले रहे हैं हम?
5.
8. Count.
Oh, 6. Sorry. D2 पे
1 plus 3 plus 2. Yeah. So you get 6 equivalent sp3d2 hybrid orbitals. So if you have 6 orbitals, shape क्या होगा?
Octahedral. But that is if you have 6 bond pairs. Sorry.
अगर bond pairs, even if
octahedral
you
ही
have
होगा.
lone pairs, the lone pairs are going to occupy like electron geometry, तो octahedral ही होगा ना. So where you find the electrons. Yeah. ठीक है. Now there is a variation in sp3d and sp3d2. There is another kind of hybridization called dsp2 hybridization. Now the difference between, like, why is the d before the sp2? What this signifies is that abhi tak humne, like sp3 mein the 2s and the 2p orbitals have taken part. sp3d mein, if you consider phosphorus, the 3s, 3p and 3d orbitals have taken part. dsp2 के केस में, when the d orbital belongs to the inner shell and sp2 s and p orbital belong to the outermost shell, like you will find d2sp3 and dsp2 mainly in the case of d block elements. So only metals are capable of this hybridization, because if you consider a structure like iron, so iron का configuration valence orbitals कौन से है? If you take the configuration of iron,
The d orbital.
3d orbital and 4s orbital. हाँ, right?
Yeah, but the thing is 4s, but you count
4s2, right? Yeah. So when, especially when they form like coordinate compounds, coordinate bonds may I had discussed, like you form something called complexes, जिसमें ions like Cn minus or H2O, जहाँ पे भी whichever has a pair of electrons to donate, both electrons in the pair is donated by the same ion. So in cases like those, D block elements mainly, not even S block metals. S block metals will not form this, non-metals will not form this. D block metals will form D2sp3 and dsp2 hybridization, क्योंकि the d orbital that is taking part in hybridization is coming from the inner shell, like 3d and 4s and 4p are taking part. But if you compare sp3d2, this is usually undergone by non-metals like sulfur, phosphorus and all. उनके केस में 3s, 3p, 3d orbitals are taking part. So spd belong to the same shell, but d2sp3 में d is coming from the n-1 shell and s and p orbitals are coming from the nth shell. That is the main difference. But otherwise, d2sp3 and sp3d2 are forming 6 hybrid orbitals, so their geometry and everything will be the same. Only the participating atomic orbitals are different.
Okay, ma'am. Got it.
Okay. Oh, there's a how to solve. I will quickly go over this. So how to figure out what is the hybridization and bonding in molecules. First step, identify the central atom, write the electronic configuration. Wahi kiya. Second step, you can draw the Lewis structure, like in the case of organic molecules. C triple bond CHH लिखा था हमने, ईथेन के केस में भी लिखा था. So Lewis structure करने पे it'll be easy to identify कितने bond pairs कितने lone pairs है. And third step, get the number of bonding pairs and lone pairs. That's exactly what I just said. So this gives the number of hybrid orbitals required. So H2O में central atom has 2 bond pairs, 2 lone pairs, hence it requires 4 hybrid orbitals. This is totally what I just discussed. Good.
I'm sorry. Doubt.
Yeah.
So the number of electron pairs is equal to the number of hybrid orbitals. Can I say that?
Yeah, I would say just be careful, because in the case of ethyne, number of electron pairs, you'll need to not consider the pi bond in that case.
So I should only consider if it's either like lone pairs or like sigma bonds.
Yes.
Okay. And if there is a pi bond, can I consider it a super bond?
Yeah. Either consider it as a super bond or like don't consider it. Basically, yeah.
Okay, ma'am, got it.
Okay. Type of bonds, single bonds, and the first overlap in double and triple bonds are always sigma bonds. So agar double triple hai, to always there is going to be one sigma, and then the subsequent ones, like double may the second one and triple may the second and third one, are going to be pi bonds always. So hybridization may, one sure shot way is check how many sigma bonds you have. Sigma bonds plus lone pairs. So usse aasan ho jayega. Okay. It is exact 5 o'clock, you guys. We still are yet to do molecular orbital theory. And if I look at the schedule, I think we've got 2 more classes. How are you guys with organic chemistry? Total positive, negative? Like, are they ions? Partial.
So
Yes. So because of
electron density of an element is distorted, it can be temporary or it can be permanent. And when it's distorted, there is a partial positive charge on one side where electron density is less, and partial negative charge on the side where electron density is more concentrated.
Correct. Now, what do you know about positive charges and negative charges? When you have positive and negative charges in the same place, what will you end up with? Like positive charge, negative charge, unlike charges hai na? So when you have unlike charges, what happens between them? Attraction. Yes. So hydrogen bonding may, so basically when you have a molecule like HCl or water or HF, so when one of the atoms is hydrogen and another atom is highly electronegative, what happened? Yeah. So when one is hydrogen and the other is highly electronegative, you end up with dipoles. Like HCl may you have a permanent dipole because chlorine is going to attract the electron pairs towards itself. HF is a permanent dipole because fluorine is going to attract the electron pairs towards itself. Water is also a permanent dipole. So when you have multiple HF molecules, like if you take a HF test tube full of HCl or HF, obviously there's going to be like so many molecules. Now each of those molecules has a partial positive, partial negative charge. So when the partial positive charge on hydrogen is attracted to partial negative charge on fluorine between different atoms, so there's like a faint sort of bond created between them. It's not a full-fledged chemical bond because they're not sharing electrons or anything, and it's not a full-fledged ionic bond because they don't have full charges. Because they are partial charges, there's like a partial bond created between them. Yeah, so that sort of bonding is called hydrogen bonding. That's all there is to it. But because of this hydrogen bonding, there are certain consequences. So one of the consequences, when, again, this is the kind of bond that is present between two different molecules, right? तो अगर दो अलग molecules में bond है which is obviously stronger than van der Waals forces क्योंकि charges के बीच में bond है, it's not solely on the basis of their masses, then will it take more energy to break them or less energy to break them?
Ma'am, can you repeat your question again?
So when you have a partial bond between two different molecules, so intermolecular bond बना हुआ है, तो if you had to break that bond, like when you're converting solid to liquid or liquid to gas, you have to break the intermolecular bonds that are there, right? So for that purpose, will it take more energy or less energy?
I mean, it should take more energy because it's intermolecular and like the attractive forces is like comparatively high.
Exactly. It takes more energy, matlab, what will it, what happens to its boiling point, melting point, etc.?
If it takes more energy, that means its boiling point is high.
Yes.
I mean, higher energy is required, and
Yes.
melting point also is low.
Melting point also
It's
will be high, like more energy
high.
is required, right, to break them. So that is like a main consequence of hydrogen bonding कि that particular compound or that particular substance का boiling point, melting point is greater. So this you observe mainly in the case of organic molecules. So even if the mass of both the like molecular mass अगर दो compounds का same है, then expectation is that their boiling point should be almost equal to each other. But if one of them has hydrogen bonding and the other does not have hydrogen bonding, then जिस molecule में hydrogen bonding है उसका boiling point या melting point will be much higher than the other one, the counterpart one. So that's like a consequence. Then there are two types of hydrogen bonding. One is intermolecular hydrogen bonding and the other is intramolecular hydrogen bonding. Okay. Again, in the name itself, inter matlab between two molecules, two different molecules. Intra matlab within the same molecule. So you can see the image here. So this particular molecule is called para-nitrophenol. So para basically indicates that they are present on opposite sides, the OH group and the NO2 group. So
the 1/4 thing.
Yeah, correct. So 1,4 position में है, तो it's called para. And this is called orthonitrophenol. So if they're in 1,2 position, adjacent atoms पे है, so it's termed as ortho. Now both of them have the exact same number of molecules, exact same atoms also, just that their positions are different. Okay, isomers. So they will have equal masses, which means that their melting point या boiling point should ideally compare to each other. But because para में यहाँ पे जो oxygen है has hydrogen bonding with the hydrogen of the other molecule, इसमें intermolecular hydrogen bonding है, which means that there is a bond between two different molecules of this compound. But ortho में, now because of this kind of geometry that they have, these two are close enough to each other that there is hydrogen bond between these two atoms in the same molecule itself. Yeah, so that's the main difference between intra and inter. So between intramolecular and intermolecular, दोनों के केस में, in which case can you expect greater boiling point?
Intra.
Boiling point matlab physical, हाँ. So between two molecules, right? Yeah. So if you have to convert this into a gas, you need to break the bond between these two molecules. But you don't have such kind of issues in intra, because whatever hydrogen bond is there, it is in the same molecule itself. So this can escape as a gas on its own, still retaining its hydrogen bond essay. Okay? So these are this like the main points of hydrogen bond. It's very simple. Hydrogen bonding is basically bond formed between hydrogen and another highly electronegative atom. तो highly electronegative atom is important because उसकी वजह से you have partial positive partial negative charges. That is why hydrogen bonds happen. Then the next main point about hydrogen bonding is two types: intermolecular, intramolecular. Then significance, yeah, it can alter the structure and properties of compounds. And what sort of properties? Like it'll change the melting point, boiling point, that sort of thing. Okay, these are the main points. That's all there is to hydrogen bonds. And hydrogen bonds are like very, very significant because this is what is present in DNA. How many of you have also taken bio? Like how many of you are studying biology? Mitali, you are. Anyone else?
I am.
Ishita, you also. Okay. So have you guys come across, structure of DNA and all that yet?
We have.
Yeah, we
Yeah.
have.
So then you must recognize hydrogen bonds. Yeah.
Huh.
So
Yeah.
parts of DNA are held together solely because of hydrogen bonds. So without the existence of hydrogen bonds, there would not be life, basically. Yeah. Okay. Cool. But you guys sure that MOT is not there, right? Like we can put it off for
Yeah.
later? Okay. Because if I look at NCRT ka main website, they have not deleted anything from this chapter. So,
Ma'am, but can you give me a second? I can check it on my classroom if you want to. I'll check.
chalega. ठीक है.
Mainly, it says that MOT is not. I'll check. I'll just check.
Maybe it's not there for this exam. वो भी हो सकता है. But I can understand because MOT, yeah, conceptually है, but I don't see, like if we skip MOT, you can still do other chapters. So that way, बाकी सारे hybridization and all is required. You reference that in the further later chapters, but MOT के लिए it's you won't reference that again. So
Yes, ma'am. I'll just a second. This is what is written.
is sending it.
Hence, will not be evaluating an exam. That's why we didn't do molecular orbital theory.
Okay.